Can you hear me? Mute it.
There I'm at. There's my mic.
So I can hear you, but you're not coming through on YouTube.
Yeah, now we're here. Now we should be.
Okay, can you hear me now? Heard the intro music. Oh, you had something turned, Robert?
I didn't have anything turned off, but every now and then OBS turns things off all on its own.
Oh, that's
So I'm so
unfortunate.
used to the cameras.
Can't hear Rob now.
Can't hear me now. Okay. Huh.
Okay, so you can hear Rob now?
Okay.
You're good.
Okay.
All right,
Let's
good.
start over. You ready?
Ready.
Welcome to the Cosmic Pie Podcast, episode 35, season 3. I'm
Yeah.
your host, Wayne Barkhouse.
And I'm Robert Moore.
And I'm Dean Smith.
Yeah, Dean's our special guest, which we've had many times before. We'll introduce him formally in a second here. But we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
We did explain, but those of you who probably didn't hear anything. Robert and I weren't feeling well last week. I had a touch of the flu, and now, of course, I got a cold. So just one thing after another. But you know the advantage of having it now? You get all over it before Christmas.
Yeah, that's true.
You see? So it's
Yeah.
a good thing. Now, we do have a chat feature that's running, so if anyone has any comments or questions that they would like to ask us, please feel free to use that function. And disclaimer, Robert, you want to do that?
Okay, I can do that. Basically, the opinions spoken herein are those of myself, Wayne, or Dean. They are not the opinions of the University of North Dakota. We are not official spokespeople, and so we're the ones on the hook for it all.
And now for the main event.
Ding, ding, ding,
Dr.
ding.
Dean Smith coming to us from his office in space, by the looks of it. I was going to say from the UND campus, but that doesn't look like UND campus. That's somewhere near Andromeda.
Yep.
Take it away, Dean.
So, yeah, I dropped by. I give a little update on a couple of the comets that you can see now. Have either of you seen Comet Lemmon or Comet Swan?
Yes, definitely, 100%.
Yep.
Several times.
Wayne's seen him. I have not.
Yeah.
Oh, you haven't? Oh,
I have
okay.
not.
I do recommend at least getting Comet Lemmon.
Okay.
And maybe it's good that we were delayed. So I did go out before the last podcast. We've had bad weather here, so
Yes.
it's been. I was lucky to get out at all. So I think I went out on the 18th. That was a Saturday before the last podcast was supposed to happen, and I did get a picture. And this is what I was going to show last week as a picture of Comet Lemmon. When I took this on the 18th, it was kind of under the handle of the Big Dipper. You could see it in binoculars, and it wasn't easy. And so I actually I was at Turtle River State Park. I was showing a small group of this through binoculars, and but you couldn't really see it naked eye. But you get a nice little picture of it. 5 days later, so this would have been on the 23rd,
Okay.
I went out and got this picture. And so,
We're not
We're not
yeah.
seeing your pictures.
I
forgot to share them.
I should actually share my screen. That would help.
Yeah.
Yeah.
And I
So-
can give you the full screen. We're on top of things today, folks.
Oh, yeah. There
So-
we go. Can you see that now?
Yeah.
can
So
see
which
that.
image is this?
All
The
right.
one taken
Yeah.
the early
So
on?
this is the one taken on the 18th.
Okay.
This would have been the Saturday before the last podcast would have happened.
Right.
Okay.
And then and then 5 days later, I got that, and so it was
Could-
quite a big difference.
Yeah.
So
It's definitely a little more
from here to
detailed.
here. Yeah, so basically a lot more of the tail is showing up. And so this was, Wednesday night, last Wednesday. And it was barely naked eye.
Mm-hmm.
I'd say naked eye, like kind of the Andromeda Galaxy's naked eye.
Yeah.
Okay.
So
So you can
Um,
see it if you're in the right conditions, good,
Yeah,
clear,
so
dark
you got to
space.
be out in a dark sky, kind of know where to look.
Right.
So, um, but yeah, you could see it, but it wasn't like you go out and like, oh wow, there's a comet there. Like you had to know where it was and look for it. So, but
Okay.
yeah, it was a lot brighter. The binocular view was a lot nicer. So that dust tail shows up. Um, you can see the tail in binoculars. So it's not just a fuzz ball. So,
Nice.
um, and I did manage to get a wider field, and it's interesting. All these pictures, you see the tail here, and then there's this bright part through the center. That bright part is ion tail, and so close in, they're near each other. In a wider field, you can tell that it's the ion. So let's bring up my wider field. And I noticed they were getting cropped off a bit, so let's kind of move that up. So, and so this is a
Oh,
picture
wow.
through a camera lens, a 135 millimeter camera lens. And you see the stars are little lines. That's because the comet's moving pretty quick. And so this was a bunch of pictures stacked. I think this was about 20 minutes worth of 30-second exposures.
Nice.
And usually in a camera lens, I just stack on the stars because it's wide enough field, the comet doesn't move. But when I did this time, the comet was a noticeable it moved. So this is basically motion blur from the comet. Um, and the comet's moving to the upper left, and it's kind of neat with the stars like this because you can kind of tell the motion. The ion tail always points away from the sun, and then the dust tail kind of bends back a bit, where it was. So the solar wind is pushing that ion tail back. It
Yeah.
doesn't push the dust tail back as much because those are heavier, dust particles. Um, so so you can kind of tell that motion leaving the dust behind in its path. And so yeah, that bright part in the telescope picture, right? We're basically looking at this section right down in here, the telescope picture. And that bright part here is the ion tail. And it's a long tail. Binoculars, you can see the dust tail. I couldn't see the ion tail. That's a lot harder. So
Right. It looks a
um,
lot brighter in these pictures, but it's really not.
yeah. So yeah, I think that yeah, it looks yeah, it looks bright here, but yeah, I think in binoculars I didn't notice the structure like this. So
Okay.
you see a bright fuzz ball and then just some fuzz, shooting back. So yeah, I wasn't seeing anything like this, in binoculars, you know. So Comet Swan, I haven't gotten a good picture of that. Um, Partly because the software I use is having trouble identifying the comet. Comet Swan is very diffuse.
Okay.
It's basically a green blob and not much of a tail. So um, I could see it in binoculars, and it looked like a fuzzball, like a nebula would. Um, so, but it is bright enough to see in binoculars. I couldn't see it naked eye. Um, but it's a green fuzzball, pretty diffuse. So this showed a lot brighter nucleus. So this is Comet Lemmon and Comet Swan. Those are the two that are out. Both binocular. If you're in a dark sky, you might be able to see Comet Lemmon naked eye. If it's dark enough to see like the Andromeda Galaxy, you might be able to see the comet. So this Lemmon is moving fast, and we are getting near the end. So I brought Stellarium up, and I have it marked here. This is Comet Lemmon. There's a lot of these. If you just search, you might find the wrong one. So this is Comet 2025 A6
I think
Lemmon.
it's still below. Can you drag it a little
Oh,
higher?
yeah, we're cropped off. Let's
Yeah.
'Let's,
Sorry.
bring that
There
up
we
here.
go.
How's that?
That looks
Yeah. Yeah. So it's low in the sky
better.
near that western horizon. So and it's actually getting lower, at least from where we are in North Dakota. It's
Okay.
getting lower. So we're this is, you basically want to see it in the next week. Um so and yeah, it started way back, let's bring up the back when I caught that picture on the 18th, right? So 10 days ago, and it was back here. So,
Oh,
uh,
wow.
so, so the 18th I caught it here, and then the 23rd I caught it here, just to the west of Booties. And in fact, I use this star here as my guide, and now I lost it, but luckily it's there. Um, but yeah, now it's cruising. It's over here now. Um, so not as obvious constellations to kind of help you find it. So, yeah, you'll want to catch it soon. It's straight west now. This is 8 p.m. You want to get out by 8 p.m. because 9 it's getting low, right? So
Right.
you want to get out by 8 p.m. That's kind of the sweet spot between being dark and high enough in the sky. Comet Swan is in the south, and we are getting a moon now. So it is, and this is R2. There's actually more than one 2025 Swan. So if you search for it in software, it's 2025 R2 Swan. And so it's actually higher in the south. So we'll be able to see this for a while. It's getting higher in the sky. But it is diffuse, not showing much of a tail. And so not nearly as exciting, I think, as Lemmon with the big tail on it. There's lots of nice pictures that people are getting of that tail from Comet Lemmon. So as long as you're out, probably see Saturn is out. And I think you talked about we are at this ring plane crossing, so the rings are pretty thin on Saturn. I did manage to catch one of the Titan shadow casts. So this is a picture I got on the September 20th. So you can see the thin rings. Every 15 years, we get these thin rings, and during those times, Titan can cast a shadow. So there's a shadow there, and then Titan is a little blur underneath. And the shadow was visible, so I saw it visually in an eyepiece. So that was
Nice.
kind of neat. And so, yeah, I actually did get it in 2009, but the scene was really bad. My picture wasn't good, and I couldn't see it visually. So I was happy that I had good scene. I was able to see it visually this time. Got a much nicer picture. So,
Okay.
and if you're out looking for comets and you got your binoculars out, because it's mainly a binocular comet, both of them. Nearby we got Andromeda, and I mentioned you can sometimes see Andromeda naked eye. So this is the square of Pegasus up here. We got Andromeda down here, and I can mark it. There we go. So there's the Andromeda galaxy, and if you can't see it naked eye, you can see it in binoculars. As long as you're out looking for comets, you can see a galaxy as well. This is kind of the prime, October is kind of the perfect time for looking at that. So,
Cool.
so that's all I got. I kind of want to give a little update on the comet. If you haven't seen it, I recommend it. Bring out a pair of binoculars. So yeah, because it's not that one last year, that Suchin Shan, I probably butchered that name. We could see that naked eye from campus at one night. So,
Right.
but this is not like that. This is in a dark sky, barely see it, but really nice binocular comet. So
Cool.
Did you get an image of Comet Swan?
I did. I forgot to bring it with.
Okay.
So, yeah, I did. It's a green fuzzball
Right.
with not much of a tail at all.
Yeah.
Is that
So-
because the tail is pointed away from us?
Yeah, I wonder. I didn't check if that was the case.
Right.
If we're just looking down, right down the front of it, or
Yeah.
so.
It's also entirely possible if it's a green fuzzball that the tail is so diffuse that it just doesn't have enough surface brightness.
Yeah, it is. It has some good size, right? That the size of that green fuzzball is bigger than the front part of Lemmon. So,
Okay.
Now, when you look at Comet Lemmon, when I was looking at it the middle of last week, the Comets that was really bright in the center, not quite star-like, is a little bit bigger than I would say the typical
Yeah.
size of a star. You noticed that too, I guess, through your telescope.
yeah. So the Comet. Yeah, it's the front is very very bright on Comet Lemmon, where Swan was a lot more diffuse and dimmer. So
So the image you're showing, you got that with your C star?
yeah, so this was the C star, that little smart telescope.
Yeah.
And so it's in the database. So you just tell it, go to Comet Lemmon, and and it starts taking pictures. And yeah, it went and started taking pictures while I was setting up my camera to do the wider field shot.
Right.
Okay.
So yeah, so by the time I got that camera set up, the C star was already taking pictures. So
I've heard
Yeah.
others that have sea stars mentioning the same thing, that while they'll set it up and let it roll while they're setting up their bigger telescope and
Right.
still get some wonderful pictures.
Oh, yeah.
So,
yeah, this was short because notice the stars are all points and everything's pointed.
Yeah.
This is only like 2 minutes. I forgot. I did do a longer one stacked on the comet. And so, or maybe I did show this. I already forgot. So this is stacked on the comet. This is basically the same data, but longer exposure. And it actually doesn't look much different, except that I think that ion tail shows up a little bit better.
yeah.
So especially as you get further back. But the stars all kind of blurred away. That bright one is here as a little line. So this is stacked on the comet, kind of after the fact. The C star won't track and stack on the comet, so you have to do that yourself, with different software. So, but yeah, just in like 2 minutes, you get a nice shot.
So where did you go to take the images? Did you stay in the city or did you go outside?
Oh no, this was out of town. This is at
Okay.
that Kelly Slough, 10 miles west
Right.
of town.
Yeah.
And then the other one on the 18th, that was out at Turtle River State Park.
Okay.
Okay.
So
So if you want to make good observations, try to get away from city lights as best as
yeah,
possible.
especially if you want to get a look at it, I'd get out into the dark.
Yeah.
For sure, especially
So-
for sure if you want to see more of the tail.
Mm-hmm.
Yeah, you probably, I'm sure, this probably visible. It's bright enough to be visible in binoculars in town, but yeah, you get more of the tail if you get into the dark.
Yeah, for sure.
That makes sense.
Yeah.
Yeah.
I mean, we've had bad luck with comets in the sense a lot of them has been near the horizon. You noticed
I've noticed that.
in the last little while,
Grumble,
right?
grumble, growl.
Yeah.
Yeah, and that's the other thing with this. It's kind of low in the west, so you might have to get to where you just have a clear horizon to look.
Yeah.
You
Right.
might have trees and stuff depending on where you're at.
It's been a while since we had one like directly overhead.
Yeah. And yeah. Mm.
Yeah, this would be nice. Hopefully,
It
it's one
would
of
be
these
nice,
days.
have a nice bright comet come overhead in the
Oh, yeah?
north. I mean, the south is getting all the good ones lately.
Yeah, I know. It's been disproportionate in the
Yeah.
talk to God, whoever's causing this.
Right.
You got to turn on
Yeah.
those rocket engines to get the comet to move so we can have a better view of it.
That's right. Southern hemisphere gets enough. Thank you.
Exactly.
Yeah, they seem to be getting them lately.
Yeah.
Yeah, we're just in the wrong spot. But we could move down there, then they'd all come up here. You know how it
Right,
works,
right. That's how it works.
Yeah, for sure.
It's like getting a new telescope. That's the surest way to summon rain.
Yeah, for 2 weeks. Okay, well, thank you, Dean. Really appreciate it.
Yeah.
So we have to leave you go because you
Welcome.
have things to do and people to see probably and
Something like that.
something like that. So thank you very much for participating today.
Yes.
And Rob and I will try to figure out how to survive without you.
Yep.
Okay.
Okay, thanks a lot, Dean.
Thank you.
Yep. Bye.
Bye. So, Robert, speaking about comets,
Yes.
bring up the one that everybody's talking about, will you please?
Do I
Intro
have to?
music. Do, 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 do. Sounds like Jaws coming
Okay,
or
okay.
something.
Here we go.
Okay, so now we're going to do an update on Comet 3i Atlas. You know, the one that's really a spacecraft?
Yeah, yeah.
And don't you dare say that, well, it's plausible, it could be anything. Could be a sneaker.
Uh-huh.
It could be a hamburger. No,
You know,
it's
somewhere out there in the universe, there is a process that produces right Nikes.
yeah, somewhere on this planet.
Yeah, there we go. Produces
That's
a
what
whole
you-
lot of left
yeah.
Nikes along with it. But
Yeah. Well, if you're lucky, you can be in the right spot in the ocean and actually see them floating around. You know,
Right.
the container ships once in a while. Now, that once in a while, you've seen that, right? With all these goods is washed ashore,
yeah,
and that includes sneakers and stuff, right?
Yep.
They get storms
seen
or
that.
something and rip open those containers. I imagine what the big hurricane's doing. I wouldn't want to be in a container ship going through that right now. Category 5 storm. So
right.
nasty
I imagine
stuff.
they're steering well.
Oh,
clear of
yeah.
that bad boy. It's
not like the old days you
180
could-
mile an hour
Oof.
sustained winds.
Yeah.
Holy cow. Anyway,
Yeah.
but Comet 3i Atlas. It's not hiding behind the sun, folks. We can still see it.
Yeah, so relative to our point of view here on the Earth, it is near the sun and just past the, if you like, closest to the sun as viewed from the Earth. In terms of its orbit, it's actually going to pass the closest to the sun tomorrow, October 29th.
Okay.
And that's when some people have suggested it'll do its Oberg maneuver and fire its thrusters and put it into a different orbit and launch probes, and they'll all, you
Yeah.
know, whatever they'll do.
But, it's not hiding behind the sun, folks. As you can see by that yellow line, it is still in view of SOHO and other space solar telescopes. So we're still watching it. Actually, this isn't SOHO, that's CORE.
Yeah.
Oh,
This data is from the NOAA National Oceanic and Atmospheric Administration satellites,
well,
GOES satellite. Yeah, this is not SOHO.
okay.
But the interesting thing, too, on this is that we can't observe the comet from ground-based telescopes right now because it is too close
It's
to the
too
sun.
close to the
And
sun.
you don't want to take a chance and damage your telescope.
Right.
So you have to wait. And plus, it's so bright, the sun, obviously, with swamped light coming from the comet. So you got to wait until it gets far enough away from the sun that's safely to observe it. And that won't be till December, early December is what I'm
Right.
hearing. So we have another month to go before we get some more pictures taken from ground-based instruments. You notice there hasn't been really anything in the news media about stuff taken from Mars? There was that little bit
Oh,
that we
yeah,
talked
that was
about
that
on our
little
last
bit.
podcast.
That's because they're being a lot more careful, and the government's still shut down.
the government's still
so
shut
nobody's
down.
working on it.
Yeah, so we have to wait for all those results to come out. Anyways, I'm still waiting for you guys to claim 100% of this. Okay, I'm claiming it's 100% a comet.
Yeah.
You have my official word. That is 100% a comet.
I mean, yeah.
And I don't
it's
mean
got
the
a
stuff you
tail
put
and
in the
everything.
sink to clean it.
Yeah,
I mean,
it's
it's
got
a
a tail
comet.
and everything. So
Yeah.
it has a coma. All the hallmarks of a comet.
Walks like a duck.
Talks like a duck. Quacks like a duck.
Yeah.
Yeah.
So
That said, as I've said before, we had a little trouble come about, but yes, it's definitely from outside the solar system, but it's still acting like a comet, so it's a comet. So
okay, order away.
yeah,
Why does it have to be crow? Can't we have deer meat or something?
yeah,
You know?
or I don't know, rabbit,
Venison.
Hassenpfeffer would be great.
Yeah. Anyways,
Anyway,
so
so
we'll see what happens.
we'll
But-
see what happens. But what's this one showing us then?
So this is a light curve that people recently a person put together, and the credits given in the bottom right of data taken from various spacecraft, one that you mentioned,
Yeah.
and others. And this shows two models, one following the brightness enhancement due to the dust part that's in the coma, and then due to the gas. So the dust is the red curve that you see there going from one side to the other. It's on the lower of the two. and the green dash curve, the top one, that's just using gas. So different properties that you put in your model, and then to estimate what is the typical increase in brightness as the comet gets closer to the sun, and then also, of course, closer to the Earth, and
Right.
changing our perspective. When the distance increases, it gets fainter, of course, but also when it gets nearer the sun, it can get brighter because of more of the activity and the outgassing that happens. Now, this object is following the prediction of the light curve. You can see all the observations. There's nothing mysterious here at
Yeah.
all. So it is doing what comets do. And so there's nothing that would suggest otherwise. So it's all intents and purposes, this is a comet.
Yeah.
It's nice
And-
to speculate about other things. Just in some sense, it gets people hyped up about astronomy, but really for the wrong reasons.
Right.
So we have really what bothers us is the fact that an individual claims with 30 to 40% confidence
Yeah.
that it's a spacecraft,
And
there's
because of his
absolutely no evidence
association-
for it at all.
Because of his associations, it's taken as, oh, that means, and it's like, no, he's talking out of his posterior.
Don't say it. Don't say it.
You know. But we are asked the question, wasn't there outgassing without acceleration? Comets don't do that, do they? And the answer is absolutely they do it. Halley's Comet outgasses and does not accelerate.
The other thing,
it's the
think
mass of the comet.
well, just think of, okay, outgassing. Think of, they act like miniature rockets, right?
Right.
Let's say you had outgassing occur in a couple different places on the comet. Well, they could be in such that when the combined thrusts come to cancel each other out, and you don't have much of an acceleration anyways.
Right.
Because it's a force we're talking about, which is a vector, which means you have to think about the strength or magnitude of that vector, but also the direction matters. So you've had two rockets, a Saturn V attached to one side of the comet and a Saturn V to the other, and they're pointed in opposite direction. You fire them, and they produce the identical thrust. That comet ain't going anywhere.
Right.
They cancel each other out.
But it is still outgassing.
Yeah.
And the other thing is if it's massive compared to the amount that it's outgassing, it won't produce a noticeable thrust. So, yeah.
That's right.
Yes, all indications are that this is a fairly massive object.
Yeah. And comets do change their orbit because of outgassing.
Right.
That's well known, right? It's just that the orbits don't change dramatically. That's the thing.
Right. And, there have been some that do change dramatically, but
Well, you have to
are
wait
no-
a long period of time.
I should say noticeably, but it's over a long period of time, and it's generally speaking small comets, small bodies, so that even a tiny thrust produces a great acceleration.
Well, you just look at Newton's law of motion, F equals ma. So a force that's applied, the amount of acceleration you get depends on the mass of the object. The
Yeah.
smaller the mass, the smaller the acceleration with a given amount of force.
Yeah,
That's all you have to look at.
And-
Over time, the stuff can accumulate, right? Objects, right? We know the effect where asteroids and stuff will emit photons because they're heated up by the sun as they're rotating
Right.
in a preferred direction. There's accumulated net, quote unquote, thrust on the object. So they'll alter their orbit slightly over time. If you wait long enough, that discrepancy builds up and builds up.
Yep.
And those kind of things. But these are all natural type of processes. There's nothing unnatural here. There's nothing that's due to
Yeah.
an
And-
intelligent life or anything else. So
and
it's not 40% confidence. That number
it's,
is wrong.
It's one individual saying,
Yeah, that it's 30, 40.
he's that confident, and it's
No.
like,
We're saying there's a
without-
100% chance it's a comet. There's a 0% chance
Yeah.
it's a spacecraft. There's nothing to see here.
It's like if you make an extraordinary claim, hey, this is an artificial body, you have to provide the evidence before that claim even needs to be considered. And that's what's going on here. We've got people that are saying, hey, this is what this is, and providing absolutely nothing out of the ordinary or in evidence to support that. And expecting then getting upset when people say, no, sorry.
Yeah.
So that's all we're doing. We're saying you want to claim that it's something extraordinary, bring on your evidence. Until then, it's this.
Yeah. It's like I often wondered if Robert here beside me is actually Bigfoot.
Right.
And they've been spotting him once in a while running through the national parks in the United States. But I would say there's probably 100% chance that Robert is not Bigfoot,
Right.
even though he has big feet compared to mine.
You know, that's all we're saying is in the face of evidence that says it's one thing, I'm going to say it's that thing. Yeah. I'm not going to go looking for an alternative until I see something happen that says, oh, we need to reconsider. And nothing like that has happened.
Yeah, and that probability numbers that people have given are just way, way, way too large.
Right.
There's no way you'd say 30 to 40%. I mean, come on. So just to say that, you're being disingenuous. That's just ridiculous.
Right. You're saying something to get clicks on a news site.
Yeah, that's all it is nowadays.
And I know that sells advertisements and gets people worked up and talking about things. And I'm all in favor of people talking about things, but when it comes down to it, you have to be reasonable about your discussions. Otherwise, you're speculating. And as an author of speculative stories, I have to say, let's speculate all you want, but let's call it that. Let's call it exactly what it is, speculation. What if? You know.
And the other thing too is with the Vera Rubin telescope, which will be in full operation. The latest I heard was today. It will be at the end of December, so the end of this year. We can potentially find a lot of these objects. So we're going to go through this same process every time we find one of these objects that's on a hyperbolic orbit, that's not bound to the solar system. That we're going to say it's a alien spacecraft, and are we going to keep doing that every time? And it's just ridiculous.
I mean. We're just finding more of these objects because we've got the instrumentation and the expertise to identify them for what they are now. I agree, Wayne. I think this is going to become old hat quickly now with the big enough telescopes and sensitive enough CCDs.
Yeah, like I said, Vera Rubin announced today, because I'm on part of the science collaborations.
Yeah.
Team announced that they'll be ready for full operation the end of this year, December 31st. So that'll be nice. So we'll get going on that telescope, and there'll be oodles and oodles and oodles of data that people will have to parse through. So it'll be very interesting.
And to be perfectly blunt here, honestly, this is a point that I'll be happy to eat crow on. Okay? If this thing suddenly does change direction, slow down, and come at us, holy crap, yeah. That answers a lot of questions, folks. Let's do it.
And you're not going to be losing any sleep tonight over that.
I'm not going to be losing any sleep. Yeah.
Anyways, so last time we were on, we were talking about black holes. And in particular, we mentioned the fact that there wasn't a black hole in the Large Magellanic Cloud. And what we noticed was someone had reported this a few months ago, back in April, that there is possibly a black hole
in
the Large Magellanic Cloud, but it's not confirmed, not even close. And so we looked at it a little bit more detail to see what this was all about, because we didn't report it at the time. We kind of missed that, I guess.
Yep.
And what it is based on the motion of stars in the halo of the Milky Way itself. Yep. And these we have very precise measurement, at least for some stars, from the Gaia mission. Unfortunately, the Gaia mission finished back in January of this year. And what Gaia did is it measured stellar parallax, so measured the shift in position of over 2 billion stars and our Milky Way galaxy. And one of the things that it can measure accurately is the motion of some of these objects. And from that, you can look for a collection or an ensemble of objects that have motion that's a little weird, that don't conform to the surrounding medium.
Right.
And it's like looking at the colors of objects. So this is one way you could do it in the past was easy, that you would look for, let's say, the color distribution of stars in the halo of the Milky Way, let's say. And if you look very carefully at precise enough color measurements, you find one little tiny grouping of stars that had a color that was a little different than the surrounding stars.
Okay.
And then if you look more carefully, maybe you do follow-up observations with a larger telescope, lo and behold, it turns out that they were a low-mass galaxy. So it's a satellite galaxy to the Milky Way.
Oh, yeah.
That has been done quite often from using the Sloan Digital Sky Survey, the Dark Energy Survey, and other surveys as well, looking for little clumps of stars that have little unusual properties, like color, for example.
Yeah.
So it's like looking, in a sea of straw and you find that needle, right? That needle has a different property than the surrounding straw. So that's how you see it. That's how you recognize that it's different.
Right.
So that's the kind of thing that we're doing here. You're looking, in this case, based on the motion of stars, looking for something that's weird, and it might tell you something. So you surf through the data looking for unusual things.
Right.
The diamond in the rough.
And in this case, what it is there's certain hypervelocity stars, stars that are moving out of the Milky Way with enough speed they won't fall back in. And what they noticed is that there's a group of them that aren't moving in the direction you would expect if they were coming from the Milky Way. So they were ejected, and they started looking back along their path, and it looks like they may have been ejected from the Large Magellanic Cloud, which would seem to indicate something had to give a star enough of a kick to send it out of the galaxy that fast. So if they're coming from the Large Magellanic Cloud, that suggests there's a black hole giving them that gravitational kick.
Right, and you're talking about kicks up, as you see there in the abstract on the paper, that was probably 300 kilometers per second.
Right.
That's a lot. And of course, you model all this stuff. You can simulate these type of motions.
Right.
So you kind of look around what you see today, a snapshot in time, and then work backwards to say, okay, how do these objects end up in the position they are with the speeds that they have? Go backwards to see if you can get a constraint on what is causing this type of motion. What is the progenitor, the origin of the motion? And what they, if you like, settled on was that it could be due to a supermassive black hole in the center of the Large Magellanic Cloud with a mass of about 600,000 times the mass of our sun. Now, for comparison, the supermassive black hole that's in the center of our own Milky Way has a mass of about 4 million times the mass of our sun.
Right.
So clearly this is a lot less massive. But there is a correlation between the mass of a black hole and the mass of the galaxy that it resides in.
And if I remember, this scales pretty well with the mass of the Large Magellanic.
Yes, well, this is the plot here that we're seeing.
Okay.
So what we have what's plotted here on the vertical axis is the mass of the supermassive black hole in solar mass units. So notice in powers of 10, it's a log plot, 10 to the 5, 10 to the 6, 10 to the 7, and so on. And on the horizontal axis, we have the velocity dispersion of the galaxy, which is really a measurement of mass of the galaxies. So massive galaxies are on the right, less massive galaxies are on the left. And notice the data point for the Large Magellanic Cloud, it's sort of towards the left there. So there are two different relationships that are given there from two different samples. One's in the dash bluish color and the other one's dash purple. And notice the Milky Way with its supermassive black hole and our velocity dispersion follows along better one of those relationships, but given the uncertainties, it's certainly consistent with both. And the LMC value that you see there in red is consistent with both relationship.
Yeah.
So if the LMC does have a supermassive black hole at its center, at its core, then we'd expect the mass to be as you see there. It's
About
consistent
what it
with
looks
that.
like. Yeah.
It's consistent with that.
Yeah.
And so that could be what's causing these stars to have the motion that they have. They have that kick due to the interaction of the star's orbits with the curved space around the central black hole that's in the LMC. But the other thing is this direct evidence? No, it's indirect.
Right.
And we like to have direct evidence. And one way we get direct evidence is that you can turn a telescope now to the LMC, and you probably have to go to infrared wavelengths because there's a lot of gas and dust in the Large Magellanic Cloud, and try to see if you can look towards the very center at a high enough resolution. So you can actually probe the motion of stars near the central black hole. We've done that with the Keck telescope for the one that's in our galaxy. And a person has won the Nobel Prize in physics for those types of observations in the past. But we need to do it for the one that's in the LMC. And if we can do that, if we can measure how fast stars are in orbit around the black hole at the center, then that would be, extreme evidence that would support that there is definitely a supermassive black hole at the heart of the Large Magellanic Cloud.
Right. But this is kind of what we were just talking about, too. This is evidence that you follow and say, hey, let's look at this. This is interesting. This is intriguing.
Well, this is evidence that you put in an observing proposal, and hopefully the panel of astronomers that review your proposal, think that it's worthy of
Yes.
observation, then you'll get time, right?
Then you'll get
You
the
can't
time.
just say, I think there's a supermassive black hole in the LMC, and somebody asks, why do you think that? I don't know. I'm just taking a shot. No, you got to have some evidence, right?
Right.
Because telescope time is extremely precious.
Extremely valuable.
So you don't want to give that to just anybody to do a fishing expedition.
Right,
You want to be able to give it to follow up different things that have been observed already.
right.
So
You want it to make sense. You want to get payoff more times than you fail.
yeah, for
So-
sure. So if it is a supermassive black hole at the center of the LMC, that's great because almost every normal galaxy has one.
Right.
So really, we're looking at the exceptions now, not the rule. Trying to find the ones that don't have a supermassive black hole. But yes,
I was just going to say that would be the interesting thing about this is the LMC for a satellite galaxy is pretty big, as I recall.
yeah,
Okay, so it would be interesting if it had one, but it would also be just as interesting if it didn't.
right, exactly.
So, this to me, this is an interesting thing to follow up on simply because, hey,
Yeah, I mean the
know.
LMC is about 100 times more massive than the next, not counting the MSC, the next massive dwarf galaxy. So for a mixed of terms, we'd say it's the giant of the dwarf galaxies in orbit around our Milky Way.
yeah,
But the other thing is the correlation in the figure that you see here. How does that get set up in the first place?
and that's the Nobel Prize winning question right
Is
there.
it that somehow that the supermassive black holes form first, and then the galaxy somehow forms around it, so that the black holes therefore would act like a seed for galaxy formation? Or does the natural process of forming a galaxy ultimately result in a supermassive black hole that forms in the center?
Right.
Now, JWST, James Webb Space Telescope, is starting to provide us with a lot of important information about this. And this is related to some of these objects we talked about in the past called little red dots, where they have these colors that are very red, and they're very small type of systems. And when people looking carefully try to uncover what is their true nature, we find that in the centers of these objects are these supermassive black holes. So are they the beginning seeds in which a galaxy would just build up its mass over time? So if you looked far enough back in time, therefore at great enough distance from us, we just see a lot of these type of objects around because you're looking at just the beginning of galaxy formation.
Right.
I mean, who knows? We don't
Who
know
knows?
right now. People are still looking
That's
at
what
that.
James Webb is supposed to, one of the things it's trying to do for us.
Right, but these objects are really high redshift, very far away, therefore very early in the history of the universe, and they already seem to have these supermassive black holes. So then that would let you, if you're down the path, if you like, of saying that the black holes form first, and then the galaxy forms around it, not the
Right.
other way around. But the jury is still out on that. We still have a lot more observing to be done, and a lot more evidence that we need to collect
Yeah.
to decide which way or the other. So,
Yep.
very cool.
I like it. I mean, to me, it would fit, but that's speculation. That's guessing.
Well, you have to speculate, but then you think about what are the type of observations that I need to collect? What is the type of telescope and instrument I need to use so I can check these possibilities out and hopefully lead me down the right road?
And then you also have to justify it and say, hey, this is why I think it's worth checking on this. And then you got to convince other people.
Yeah, for sure. Okay. Now, another thing we like to talk about today that's just showed up in the news recently is this paper that was published in Nature Geoscience. And I thought Robert would really like this paper because it's kind of,
Brushes
In
against
his
what I was
wheelhouse.
doing when I was trying to get a PhD.
yeah, so maybe Robert, you could take over from here and kind of describe what this is all about.
I can kind of describe what it's about. It is different enough from what I was doing that I have questions. I need to study up a little more than what I have. But basically, the Earth's constituent materials, there's chemical tracers of the parent bodies, the things that went into making it. And a lot of our theories about the interior of the Earth revolve around the idea that over 4 billion years, are actually more like 3.5 to 4 billion years, the Earth's convection of the mantle has mixed it enough that it's homogeneous, that it's the same throughout. What this paper is saying is they found indicators in potassium abundances that seem to indicate that there are places in the mantle and the crust where things have not been homogenized. They have not been made the same. And that indicates that there was a different parent body that went into making the Earth.
Now, this is the time frame before the moon.
Before the moon forming impact, yeah.
So what kind of, just so people know, what kind of effect did that have on the geology of the Earth after the moon formed? And that's due to a collision, right?
All right. You mean other than turning the whole planet into essentially a molten ball?
Well, that's what we're getting at here.
Okay.
And what would that do?
And that would, of course, allow for more free movement of convection currents because the mantle is solid, folks. It is not molten. The mantle is solid. Okay? And so right now, the convection is at about 3 centimeters per year. Okay? When it's liquid, you get more like water boiling because it can move a lot more freely. So that should have actually helped it homogenize. But what this is saying is that things are heterogeneous, that there are zones and regions that are different from the bulk mantle. And that is just interesting because how did that survive the moon forming impact and things like that? Because as of now, all evidence points to the fact that there was a moon forming impactor. The moon was not captured. It's too large.
So this impactor that hit the Earth, if I remember right, it's more of the mantle that would have left the Earth to form the moon than the deep inside inner core or anything like that.
And we know from the moon rocks that were turned from the Apollo missions and other missions that their chemical makeup is the oxygen isotopic mix is a little different and things like that, which we think means that more of the impactor body went into the moon than Earth. But it would have been Earth's mantle. So finding that there's these heterogeneities is huge.
Now, why is it always potassium-40? Maybe we should explain that.
Because potassium-40, one reason is it's a long-lived isotope, radioactive isotope, sorry. So it is radioactive, but it's radioactive on the order of hundreds of millions of years. So it's still present, it's still traceable. Number two, it's volatile, so a lot of it was left from the Earth as it was forming because it was heated. And it's also a type of element that we call a lithophile element. Litho meaning rock, phile meaning loving. Potassium likes to be in rock. It does not like to be in metal. So most of the potassium, when the core formed, should have been driven out of the core, the metal of the core, and out into the mantle rock. So the mantle, in other words, should be enriched in potassium compared to what we see in asteroids and so forth. It's not. The mantle is depleted compared to these asteroids, and by enough that it's not reconcilable with volatilization, with evaporation, essentially.
Well, why would it be depleted? Was there some kind of a major shock event that ripped the potassium away from the rocks?
And there's the question, isn't it? Why would it be depleted? And part of my research was actually looking, could some of it be in the core? Could the composition of iron and nickel with these other light elements, usually considered to be hydrogen, sulfur, oxygen, or carbon, that combination of light elements have drawn in, made more siderophile, metal-loving, the potassium than we would expect. And so
you're thinking like a contamination effects?
Right. So, more than we expected could have been drawn into the core.
So some type of catalyst then
Right.
would increase the bonding.
Because, another tracer they look at is uranium, because we like the long-lived radioactive isotopes because that would provide an energy source for driving the magnetic dynamo that produces Earth's magnetic field. So what's going on is if there's more, all of these elements are normally lithophile. They like being in rock. What that means is there's a chemical gradient stronger than the gravitational gradient that pulls them into rock instead of sinking into the core. because they are dense, they're heavy. So if you can alter that chemical energy gradient even a little bit, you get more sticking in the core.
Now, if we go to the next slide, we can, in graphical form, see sort of measurements that were taken of the potassium, and looking at what looks like, you know, how off they are from the mean or average value in some sense, right? So little like epsilon type of stuff, right? So little perturbations away from the measurements. So maybe you can explain.
Okay,
to viewers
some
what's
of
going
these
on
terms
here.
I can explain.
Okay.
Some of them I'm afraid I can't. Like OIB that you see next to that pink bar on the left graph is ocean island basalt. So it's basalt rock from the ocean islands like Hawaii. Then there's Morb, which is mid-oceanic, if I remember, mid-oceanic ridge basalt. Yeah, that's it. Sorry, folks, it's been 5 years since I've used these terms.
Well, there's one there that's familiar to us, right?
Yeah,
So what is that? The
Winnipegosis. That's some of these terms are also related to what we call cratons, which are the root, the core of continents. It's the oldest rock that exists in the crust.
like in the Canadian Shield or in Australia.
Bingo. And so Winnipegosis
Winnipegosis.
is one of these cratons.
Oh.
It's part of the Canadian Shield.
So this is in Manitoba that it was
Yeah.
discovered, or they
Yeah,
do
so-
work on, right?
So they're looking at, bottom line, they're looking at really old rock and comparing it to material we know is coming from the mantle, like the mid-oceanic ridge, the ocean islands.
Greenland would be a good.
Greenland is a great one, and I think that's
It's probably up there somewhere.
we'll see, where is it? The new, on the right-hand graph, the Nunavut
Yeah. Okay.
is, I think, the Greenland Shield.
Got it.
And, you know, there's one here in the core of North America. There's one in Africa.
So these color bars. So on the A plot, which is on the left, you had like pink color, and then on the B plot on the right, it's like greenish or lime color. So what does that represent? Those measurements there.
Those are essentially their measurements, where they took these rocks from these certain things, like on the left, it's ocean island basalts and everything.
Right.
And they're showing this relative abundances, this epsilon 40K, which is related to a mass independent measure of the abundances. And that's the part that I'm really not sure on. How do you get a
Right.
mass independent abundance? I'm not 100% on what that means or how it is. And I hope my advisors aren't on their way to driving up here to come smack me about the head and shoulders. But yeah, the left graph is essentially where they're looking at known tectonic settings. So they're looking at ocean island ridges and the basalts that come from there, which are mantle derived. They're looking at trenches and basalts that are in the island arcs behind the trenches, where volcanism is prevalent because of the subducting plates. And then they're looking on the right at Archean sedimentary samples. So they're looking at rock from these shields, these cratons. And both are showing this epsilon K, but they're different. And they're not in that gray bar where they should be, where we would expect them to be for the Earth to be assembled from what we call various types of chondritic asteroids, which are the oldest rocks that have been found in the solar system, these chondrites.
Right. So those error bars, they said it looks like it's two standard errors, so 2 sigma errors on their measurements.
And so it's way off from
So it's
the
significantly
expected.
different,
Right.
and that's the mystery.
And that's the mystery. And so what they're attributing it to is that, yes, the original parent body of Earth was significantly different from any bodies we found in the current solar system.
And the impactor that ultimately created the moon then didn't mix everything
Didn't mix everything up
as
like
what we thought. Interesting.
So this changes a lot of, we you know, with a lot of our data and our hypotheses and our theories, we've made the assumption that Earth is homogeneous through the mantle. This is an indication that that may be a bad assumption. Now, let me be clear. That doesn't change the theories and hypotheses much. But it would have to start make you go, well, you can't exactly say this.
But doesn't that really, another way to look at it is this provides a new way of observing what the Earth was like in the mantle before the moon creating
Yes.
event happened itself.
That's exactly what it means.
Because otherwise, if it was complete mixed, then you lose all that information.
Right. And so this says we may be able to get at some of that information. That's big. That's wonderful. But again, we're back to the black hole at the center of the Large Magellanic Cloud.
Yeah.
This is indicative and great, but there are other possibilities. Now we need to investigate them. There's evidence that something interesting is going on. Let's now poke at it.
Yeah, and I guess if you can get a better measurement of elemental abundance ratios and isotopic differences and so on, isotope differences, that you can get maybe a better understanding of the pre-solar nebula and just when the Earth was forming,
Right.
and compare that to things that are much further away from the sun
Yep.
to see gradients in this pre-solar nebula itself.
Like there are the daughter products of several chains of radioactive decay that are present in chondrites and chondrules and on Earth that let us know that there were a couple of supernova that cooked off while the solar system was forming.
Yeah, this aluminum takes.
It's aluminum 26 and one of the isotopes of tungsten.
Right. Now you said a term that where the continents are anchored to the Earth, cratons or something.
Cratons, yeah.
So what is the craton exactly?
Craton is it's the oldest rock in the oldest crustal rock.
Okay.
So bottom line, when the crust started forming and solidifying, which happens because there's a lot of elements that don't even like being, they're rock loving, but they don't like being in mantle composition rock, because that's something a lot of people don't realize either. The crust is chemically distinct from the mantle. It's not just that it's solid, which again, the mantle is solid itself. It's not liquid. But there are chemical differences. This is how we know that some rocks that we find on the surface, well, this is mantle material, because it's chemically nothing like the crust. So when you age the crustal rock, what we found is that there's these units, these cratons, these blocks of rock on usually underground, deep at the heart of the continent, that exist, and they were given the name craton because
Isn't that what you have in your salad?
no, that's crouton.
Oh, okay. Something else.
Crusty old rock. Funny you should mention that. I remember I mentioned that I wrote speculative stories.
Now, what about plate tectonics?
So-
What's their role in that?
Their role in that is again, they're the hearts of these continents. They're floating around essentially on that solid mantle. You got to think of the mantle more like a sand pile.
Right.
So you can float along on top of it, and these things are such that unless a craton impacts onto a craton, they're not going to subduct.
Okay.
Okay.
Right.
So they're bottom line, they're the most stable places on the continent.
How far down are they typically?
They go down to the mantle. They
Wow.
are
So there's no way you can drill down and get a sample of them in the.
they go down for
future?
like 60 kilometers. So
Right. Because that would be interesting to get a sample of the material, right?
right, I agree. But
How do you
where
do
we're
that?
trying to penetrate into the mantle, actually, there's a few places on the Earth's surface where the mantle is exposed.
How far down can we go? Like 10 kilometers or something?
Something
Or
like
is it
that.
longer than that?
And at the ocean ridges, or near the ocean ridges, the crust is only 3 kilometers thick. So we could easily drill that, except it's 5,000 feet down in the ocean.
Right, yeah, right.
So, but yes, there are plans that keep coming up where people are trying to
Wasn't like
do that drill.
the deepest hole ever made or drilled was done in Russia or something?
Yes.
And where we got Halloween coming up and we need to wrap up, I heard that when you open up the lid of that hole, you can actually hear, if you listen really carefully, you hear all kinds of people down in the hole screeching and hollering.
Yeah, everybody says that. And
Like they're in
play
hell.
recordings of
Like
it
they're in
and
hell,
everything,
right?
Yeah, and it's like, no.
The devil's
There are
hole.
no such
The
recordings.
devil's hole.
Yeah. But, I'll end on this. The reason we also can't drill down that deep is because the pressure becomes so great that it crushes anything we're trying to put down the hole.
Right.
You got to remember, pressure goes up as you go into the
You mean
ground.
the
too.
movie Core is not real?
The movie core is not real.
We'll have to say that for another time, right? Anyways, thank you very much for watching this podcast. If you want to learn more about the STEM field, so science in general or anything else, you can come to the University of North Dakota. We have classes both online on campus and lots of different programs, and hopefully some of it interests you.
Yep.
Our next podcast will be, assuming that we're not sick, knock on wood.
Knock on
You
wood.
can hear that, hopefully. Will be next Tuesday, so that's November the 4th.
Already?
November already. It's going fast. And so we always leave a quote at the end of our podcast.
Okay.
So today's quote is by Vincent van Gogh. I'm good thing we're ending because my voice is almost completely gone at this point.
Yeah.
So here's a quote by Van Gogh. For my part, I know nothing with any certainty, but the sight of the stars makes me dream.
Nice.
And with that, please give us a thumbs up, subscribe if you haven't subscribed, and we'll see you next time. Thank you.
See you, folks.